Hello class, this is the lecture video to finish off section 2.3. Before we introduce a new idea, I wanted to go over this current problem and do it in another way that you might find easier or more intuitive. One of the weird things about this solution that they do here, so we're trying to find the equation of the plane spanned by those. You can ask yourself, okay, what combination of C1 and C2 do I need to get any x, y, and z? And so you can augment the matrix like they do here, and then you row reduce it, and you get this one. But from what's written right now, you may be wondering, like, why pull out the middle one as the thing that would help us find the equation of the plane? Well, C1 and C2, so if we rewrite all of these based off of C1 and C2, then we have that C1 times 1 minus 2 times C2 equals x, and the bottom one would be C2 equals z minus 3x, and the middle one is 0 C1s 0 times C1 plus 0 times C2 equals y minus 2x. Now, you'll notice that this first and third one depend on C1 and C2, but this middle one does not. So this middle one here, it doesn't depend on that because this left-hand side is just 0. And so that's the reason they pull that one out, is because it doesn't depend on C1 and C2. It gives you a relationship that has to hold for everything independent of what C1 and C2 are. So that's the way they pull that out. I was more comfortable doing this a different way when I was in your shoes. So that way uses dot products, and it goes back to the fact that if you have an equation of this form, then the coefficients a, b, and c make a vector that is normal to the plane. So we can use that fact and use a dot product to set up a system of equations to solve. Both ways you're solving a system of equations or reducing a matrix. But for a, b, and c, I know that a, b, c dot 1, 2, 3, which it has to equal 0. And I also know that a, b, c dot a minus 2, a minus 4, and a minus 5 has to equal 0. And I'm searching for a, b, and c so I can plug it into this general form of the equation. And after I do the dot products, that just means that I get a plus 2b plus 3c, and 0 equals a minus 2a, a minus 4b, and a minus 5c. And so I have two equations to work with. I have that one, I have that one. I have two equations and I have three unknowns. So some of you may be thinking, Brother Corey, you don't have enough information to solve this. And I haven't got D in there yet anywhere. So where's D going to come in? Well, there is another piece of information that we have, and that is it goes to the point 0, 0. If we're spanning with these vectors, they're going to be in standard form. They didn't tell us another point. So these vectors are going to start at 0 at the origin. So I actually already know that D has to be 0. But we'll come back to that. Forgot to include 0 in that box. All right. But we still have three unknowns, A, B, and C, and we still only have two equations, so it seems like we'd only be able to solve for two of them. We're going to have infinite solutions. Well, that's true because A, B, and C are not unique. A, B, C, and D are not unique. If I multiplied both sides of the equation by any number, non-zero, I would still have the same equation of the plane. So we could go ahead and just define A to be 1, and then we could find B, C, and D in terms of find out exactly what B and C would be. But I'm going to choose later what A or B or whatever equals, because sometimes if you pull it out to be 1, then you're going to end up with some crazy fractions for B and C. That's okay. We should be comfortable with crazy fractions. So I'm going to augment this matrix. So 1, 2, 3, a minus 2, a minus 4, a minus 5, 0, 0. Okay, and let's reduce it. So I'm going to multiply the numerator by a minus 2. Not the numerator, the upper row by by 2, and add it to row 2. And so we get 1, 2, 3, 0, 0. This will become a 0. This will become a 0. This will become, I'll have 2 times 3, which is 6, minus 5, which will be 1. And now I can use this pivot column here, this 1 in the second row, to get rid of the 3. So I can multiply it by minus 3 and add. Because I have zeros everywhere else in that row already, that's the only thing that will change, will be that value. So, and now I can think about what this solution means. So I know automatically that C has to equal 0, because if I translate that line back into an equation, it's I have no A's, I have no B's, I have one C, and it equals 0. I can also translate this numerator, not the numerator, the upper line to 1x plus 2y equals 0. So I wrote x and y. I did not mean to write x and y. I meant to write an a plus 2b there. A plus 2b has to equal 0. So I'm free to pick any value for a and any value for b as long as they add up to 0. So when I write out this equation, something x plus something y plus something z equals d, well, and I already know that since we go through the origin, d is going to be 0. I know that c is 0, and now I can pick a and b, but those two I have to have this constraint hold. So if I pick a minus 2 for a, then b can just be 1, and so I get that, which simplifies to y equals 2x, or 0 equals y minus 2x, which is how the book puts it, or how these slides put it right here. Oops, y minus 2x equals 0. So anyway, that's another way that some of you might be more comfortable with than with what this professor did. Okay. So here's a theorem. I mentioned yesterday, at least in one of the classes, that we're in the part of the class where we actually find lots of different ways to say the same thing in linear algebra. We get a lot of different ideas, and what we're doing is building connections between those. So this theorem makes a connection between some of the ideas that we've talked about. So if A is an m by n matrix, then the following statements are logically equivalent. That is, for a particular matrix A, they're either all true or they are all false. Each B in Rm is a linear combination of the columns of A. So So no matter what point we pick in Rm, then we can find some linear combination of the columns of A to reach that point. For each B in Rm, the system, this is the augmented matrix, that system there has at least one solution. The columns of A span Rm, so that means the span is any place you can get with any linear combination of the sets. And so the columns with that set of vectors, you can span Rm, and A has a pivot position in every row. All of those are equivalent. So if you know one, you know the other ones. And this, in practice, is a pretty nice way to find the other ones. You can start row reducing. So you can set it up as an augmented matrix, or you don't even need to have B. You can just start row reducing the matrix A, the coefficient matrix, and if you see you have a pivot position in every row, then you'll know the columns of A span Rm. You know any point in there is at least one solution for that, yeah, one holds also. Warning, this theorem's about a coefficient matrix, not an augmented matrix, right? So we're just talking about that one, not an augmented matrix. If you have a pivot position in every row in an augmented matrix, that may or may not be consistent, may or may not have a solution. So, okay, a new definition. Let me talk about the idea of linear independence first before we throw out a definition. So the idea of linear independence is a set is linear independent if each one is needed, or each one offers new information for the set. They're linearly dependent if you have at least one vector that you could get by making by combining other vectors. So you have something that's redundant. So in our food example from the peanut butter book, if I had a vector that represented peanut butter, like the nutritional fact of peanut butter, the nutritional fact of bread, the nutritional facts of jam, and I had another vector that represented a peanut butter and jelly sandwich, a peanut butter and jam sandwich, then this we don't need in this set. We can still, with combinations of all of these other, three, we can get the same thing whether we add this or not. So we don't really need that. So this whole set would be linearly dependent, because one of these we could make with the other ones. This set, with the values we pick in the book, they are linearly independent, but that's not clear why. You wouldn't know for sure just because of one's peanut butter, one's bread, and one's jam. It depends on the actual nutritional facts we're looking at. So sorry, kind of messing this up here. So a set of vectors in Rn is said to be linearly independent if the only coefficients of the p vectors which satisfy the equation, so here we have some combination of those vectors equaling 0. If all of those scalars have to be 0, then they are linearly independent. So how many of vector 1, how much of vector 2, how much of vector 3, dot, 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 up to vector p, how much do I need so I can add them all together and get 0? If I have to just take 0 of each one of those, which I always can to get 0, but if I have to do that, then that's one way, that's what we say is the definition of that set of vectors being linearly independent. So there are other ways of thinking about this, and we'll look at those in just a second. If there's at least one C value that is not 0, if we can combine these in some way and make at least one C value not 0 and still get 0 over here, then it's linearly dependent. So we have an extra, in some ways, intuitively, we have an extra vector, at least one extra vector that we actually don't need. We could get all the combinations that we wanted if we threw that vector out. So determine if these vectors are linearly independent. So one thing we can do is go back to our definition and say, well, are there C1s and C2s and C3 in our case that we can pick to make the zero vector? So the way they set it up is they put the three vectors in an augmented matrix with a zero, and they start row reducing, and we don't have any free variables. We do end up with three pivot columns, so we'll be able to continue solving and get a value for x, a value for y, a value for z, and since we have all these pivot columns, we're going to end up with ones down the diagonal and zero everywhere else, and so we just know that the C1 has to be 0, C2 has to be 0, C3 has to be 0. So we only have that trivial solution to this homogeneous equation. Homogeneous is if we have a system that equals the zero vector. Okay, so they are linearly independent. We can't make one by taking linear combinations of the other one. So these are three statements that are equivalent, four statements that are equivalent. This is the definition. This is the definition of linear independent that we just talked about. If we have that vector equation that equals 0 and it only has the trivial solution, then they are linearly independent. If the system, so we start writing down using the vectors and start writing them down in an augmented matrix, augment it with 0, and we solve. If it only has the trivial solution, x equals 0. Remember, this is a 0 vector, and this is a vector x and a vector 0. If that's true, then it's linearly independent. And if the matrix, if we don't augment it with 0 here, we just take all the columns, we just make a matrix with the column where the columns are each of the vectors. If it has a pivot in every column, then it's linearly independent, and that's exactly what I've been saying every time, that all those are equivalent to being linearly independent. So are these vectors linearly independent? So you can augment it with 0, but you can also you don't have to augment it with 0. You can just start with a matrix where the columns are the vectors, and then start row reducing. And if you have a pivot position in each row, they're independent. If not, they're dependent. And as the row reduction shows, hey, we've got a free variable. We don't have a pivot column in this row, none in this column. So these are not linearly independent. So there's infinitely many solutions that you could pick for C1, C2, and C3 to make those 0. We don't have to just have 0, 0, a vector 1, 0 times vector 2, and 0 times vector 3 to equal that 0 vector. Okay. So a few things that you can use as you reason through these problems. If you only have one vector, then it's linearly independent if and only if the vector is not the 0 vector. That 0 vector can cause problems because if any set has the 0 vector in it, you could take 2 times the 0 vector, or 3 times the 0 vector, or 5 times the 0 vector, and still get the 0 vector out, or still get the same combination with the other values. So it makes it really easy to find a coefficient in a set where it is not, where all the coefficients aren't 0. Right, so the question here is, if you have the 0 vector, here's our 0 vector, when will it equal the 0 vector for what combination of C? Any C. So it doesn't have to just be 0. So that's why we have this constraint. A set V and W is linearly independent if and only if either a V, if neither a V nor W is a scalar multiple of the other. If we're down to 2, if we only are talking about 2, then for them to be combinations of each other, one of them just has to be a scalar multiple of the other one. That's the only way you can get that to happen. So one might be 1, 2. If the other one is 5, 5, 6, then we actually know using this fact that they're independent because I have to multiply 1 by 5 to get 5, but 2 times 5 is not 6, so they're not. But that does not work once you get to 3 or more vectors. Then you can have linearly dependent sets, even though no one of them is a scalar multiple of another one. So it'll be one of them will be linear combinations, but not just a simple scalar multiple of one other one. Okay, are these linearly independent? Well, you just have to start looking to see, hey, is there one thing I can multiply these values by and get all of these values? Well, to go from 2 to 16, I've got to multiply it by 8. Sorry, don't know what happened there. The computer's freaking out. There. Got to multiply by 8, but a minus 1 to a minus 7, it doesn't work to multiply by 8, so they're linearly independent. Okay. So this is something I actually just mentioned. Won't spend a lot of time on this. If you have a set of vectors and they're linearly dependent, then one of them, at least one of them, can be made as a linear combination of the other ones. And you can look at the proofs there. And so here's something to think about. What happens is if you add in a new vector to a set. So here you have u and v. Here's a set of vectors. What do they span? Well, it's easy to see that u and v aren't multiples of each other, because I'd have to multiply u by 1 to get those top ones to correspond. But 2 times 1 does not equal 1, so they're not linear. They're not scalar multiples of each other, so they're independent. So they would span a plane in R3. Because you have 3 coordinates, so you're talking about R3, but we only have two independent vectors, so it can at most span a plane. So if W is another vector in R3, what will happen if we add W into this? Well, what happens to the span? If it's linearly independent, then it would span all of R3. So that means if it's independent, meaning it doesn't lie in the planes already spanned by those, then we have another linearly independent vector. We can get to anywhere in R3. But if it's linearly dependent, so that means W lies in that plane, we can get to u and v. We can get to W just by combinations of u and v. Then it doesn't increase our span at all. So. Okay. So there are some ways to quickly know if a set is linearly dependent, mainly. If we have a set of vectors if we have a set of vectors, I should have just done these as columns of a matrix, and here I have 3 coordinates for each, but I have 4 vectors. So in this case, my n is 3, right? That's the dimension that we're working in, but p is 4, the number of vectors that I have. One of those has, at least one of those has to be a combination of the other one, of the other ones. So we know automatically that it's that this is a linearly dependent set. So, because even at most, these might span R3, but then like if the second one isn't a combination of the first one, then okay, we span a plane. If the third one is in that plane, then they're linearly dependent. If not, then it's linearly independent. We have 3 vectors that would span R3. Well, here we have this point is in R3 somewhere, so we have to be able to get to it with combinations of those first 3 vectors. So it's kind of the wider than is tall idea. Here, you don't have enough rows to have a pivot in every column, right? We could only have 3 rows, but we have 4 columns, so we have to have a free variable somewhere. Okay, we already talked about that. So, which of the following sets of vectors is linearly independent? So these don't require these are sets that don't require a lot of work, showing this the power of understanding some of the ideas we've talked about so far. Well, here we're in dimension 3, so n is 3, but we've got 4 vectors. This is the case that we just talked about, so it has to be linearly dependent. Here we have the 0 vector, and so we could take combinations of these 3 and get the 0 vector out. I could have this 0 times that, I could have this 1 times that, and I could have this 0 times this one, and that would all equal 0, but not all the coefficients are 0. So, because I could have 1 times the 0 vector. And here, if you look carefully, you can see that you could just multiply this first one by a minus 3/2, and you would get the last one. So we can see that, oh, one's a scalar multiple of the other one. So they're linearly dependent. And last, here's a theorem. These following statements are logically equivalent. So they're either all false or all true for any matrix A. So A augmented with 0 has only the trivial solution, which means all of your variables all of your coefficients would be 0, like the variables will all have to equal 0. For every B in Rm, the system A augmented with B has at most 1 solution. Okay, not most. The columns of A are linearly independent, and A has a pivot position in every column. So all of those, once you know one of those, you know all of the other ones. And this is usually the method we use to figure out the other ones. So, thanks.